We want to know what is the net torque about on the bar that is shown in the figure below. We see that the bar is located horizontally. It has a black dot that represents the pivot. That's the point of rotation. There are two forces represented with red arrows, and each force has different magnitude and different angle. At the left hand side there is a force that has a magnitude of 8 newtons and is making an angle phi that makes 70 degrees with respect to the negative x-axis. At the right hand side there is a force with a magnitude of 10 newtons that has an angle theta of 60 degrees with respect to the positive x-axis. We see that the pivot is located 25 centimeters from the left edge and 75 centimeters away from the right edge. We need to convert the centimeters to meters because we are working with newtons and we need the units to match. Torque, by definition, is R cross F. R is the arm or the radius in meters from the pivot point to the location where the force is applied, and F is the force itself. Both R and F are vectors, so we can do a cross product. Or we can also say that the torque is the magnitude of R times the magnitude of the force F times the sine of the angle between them. In this experiment, we have two different torques because we have two different forces. The torque 1 is going to be due to the left hand side and the torque 2 to the right hand side. At the end of this explanation, I'm going to do a side note for you to have a better intuition of the concept of torque. I highly recommend to watch the side note at the end. Torque 1 is equal to negative 0.25 meters times 8 newtons times the sine of 70. Torque 1 is equal to negative 1.879 newtons meters. I put the negative because that force is generating a clockwise torque, and by convention the clockwise torque is negative. The torque 2 is equal to 0.75 meters times 10 newtons times the sine of 60. Torque 2 is equal to positive 6.49519 newton meters. And it's positive because that force is doing a counterclockwise torque that by convention is positive. To calculate the torque net, we're going to add all the torques. In this case, we only have two. So negative 1.879 plus 6.495 give us a torque net of positive 4.6158 newtons meters. I recommend to take all the decimal points for calculations, and at the end you can round. For example, in this case it's 4.62. Now let's go to the side note. This is going to be useful because it's a visual explanation of how torque works. So we have a propeller that's a rigid body. It has the pivot point at the center. So this is the pivot point right at the center. This is the axis of rotation. It has a force, let's say this is magnitude of F2 and this is the magnitude of F1. Both forces at different angles. We have the arm R that comes from the pivot point to the edge where the force is applied. R1 is in meters and R2 is also in meters from the pivot point to the other edge where F2 is applied. We know by definition that the torque is R cross F. Is the cross product between the vector R and the vector F. Or also the magnitude of R times the magnitude of F times the sine of the angle between both vectors. So we see that there is sine of theta. This is the opposite. We're taking account for the perpendicular components of the forces because the horizontal components doesn't matter. If you see from this experiment, What happens if I push? This is a horizontal component. Nothing happens. What happens if I pull? Nothing happens. But what happens if I use the perpendicular component of this force? You see that there is a torque. It tries to do a counterclockwise direction torque. What happens if I go the other way? This force, this component, it makes a torque, the clockwise. So this force is doing a negative torque because it's doing like a clockwise torque, and this force 2 is doing a positive torque because by convention the counterclockwise torque is positive. So you see that the forces that are perpendicular to the line of action of the pivot generates a torque, but the forces that are in the same line of action of the pivot, they don't generate a torque, just by pushing or pulling. And also, from the definition of torque, we know that if we apply the force at the edge, it's going to be larger, the torque is going to be larger, because it's directly proportional to the arm R. But if we go closer, it's going to be less torque, because the R is smaller. What happens if we decrease the R? Now it doesn't matter if I push here, because it's in the same line of action of the pivot point. That's when the R is 0. So in that case, there will be no torque. So you see, there is torque, and when R is 0, no torque. When I am in the same line of action of the pivot point, there is no torque. Only the forces that are at a distance and are perpendicular to that line of action, they produce torque. I'll see you in the next video, guys, and let me know your thoughts and comments. Bye, guys.